Welcome, this is the AP Physics video lecture. This is on Unit 4, Energy. The section that we're going to talk about is specifically potential energy. This slide that I want to go over isn't actually not on the AP Physics 1 exam. But the reason why I want to talk about this is that this slide should give you a understanding to why potential energy works the way it works. This slide gives you a understanding of something called energy states, which comes from a field of physics that connects probability, which is in stats, as well as physics, which we call StatMeg. We talk about energy states as a description of the amount of energy of a system an object has. Here, we would say that the ball is in a neutral equilibrium. This, we can say, is at the lowest energy state. Okay. This is considered to be the natural state of the object because it is the most likely state that the object wants to be in. If we take a probability, we would say that this is going to be the state that we see H2O most commonly in the water state. This is its lowest state. This is in its natural state. Then we can talk about the exciting state. This is when the ball is at an unstable equilibrium. Notice at the lowest at equilibrium, the y equals to 0. Here, this was y equals to 0, but this time there is actually a height. Because there is a height, this ball wants to come back down. The analogy I want to use, it's like boiling water. Do you normally see water boiling? No. Even after the water is boiling in the forms of gas, the gas doesn't want to stay in the gas. It actually wants to come back to becoming water. Okay? Likewise, the ball is up with potential energy. It wants to come down to its natural state. Objects do not want to stay away from equilibrium. Objects will want to move back to its equilibrium state. This we consider as an excited state. If we picked H2O out of randomly, are you going to see it as water or are you going to see it as gas? Well, probability wise, say that most likely the object is going to be in the water because that's just its natural state. It is less likely to be in its excited state. Now, there's something called a stable state. Well, this is when it is below equilibrium. This is still technically a low energy state as well, but here, and it's not due to inertia. I did not want to put inertia. It's actually due to the phrase entropy. Okay, and this is actually not due to inertia. It's due to entropy. Okay, the inertia here refers to mass. Entropy refers to the states of energy. So here we would say that an ice cube, let's just use this metaphor. If we put an ice cube out, is it going to stay as an ice cube? No, it actually wants to become water because this is in its natural state. But can ice naturally become water? Well, yes, if it releases energy. No, if it absorbs energy. Okay, energy. And if it absorbs energy, the object is going to move up, back. If it obtains energy, it's going to move up. Likewise, like this one, it wants to lose energy to go back to its energy state. Okay? This is what you want to think about when you think about potential energy. It's energy state that is away from equilibrium and it never wants to stay there. It always wants to release that potential energy so it can return back to equilibrium. All right. Now, the rest is on the AP Physics 1 exam. This is potential energy. And specifically, we talk about the mechanical potential energy. The definition of potential energy, again, is the energy that is the stored energy that can be transferred to do work. The definition of the potential energy in terms of nature and equilibrium, we would say that it is the energy stored by displacing the object away from equilibrium. Remember, only a system can have potential energy. What do I mean by that? Let's look at the two types. So the object here would be the cart, but the system here would be the cart and Earth. Why? Well, the natural state is when delta y equals to 0, right here, when it's flat. But now we plug it in, right? Mass, gravity, times height. This is gravity, and this has to be on Earth. Okay, this is the reason why you need the cart and Earth system. That's the only way you can get the G here. This is the cart. Okay, look at your nouns. You have a cart and Earth. That's what makes up your system. Now, let's say that we move the cart up on top of the roller coaster. We would say that the object actually gained potential energy by having a delta y, a height. The object got that energy because someone actually put energy into that. Someone actually did work into the system. So here, the height is no longer 0. So we would say that the potential energy is greater than 0. The system here has potential energy. And how did it gain potential energy? God? Right? Magic? No. Someone actually put energy into the system. In real life, the only way a roller coaster cart goes up is when someone uses electricity, right? And you hear that click sound, click, 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 that moves the cart up. And that is due to the electricity. So energy was being done to move the cart to some potential energy. The second type of potential energy is the spring. So here, the object would be the spring and the mass. The system would be the spring, mass, and Earth. Okay? The natural state of equilibrium is when the delta x equals to 0, which is right here. This is when delta x equals to 0. This is at equilibrium. This is the state all springs wants to be in. If you go and look at a slinky, it's going to be in its natural state at equilibrium. It's not going to be stretched or compressed. At this point, we would say it had no potential energy. Why? Because delta x equals to 0. But what happens when we compress it or stretch it? Compression is when the delta x is a negative number. The reason why it's negative is because this, let's say, would be negative 5 meters. If it's a stretch, it goes the other way, would be positive 5 meters. But it won't matter, okay? If you plug it in, no matter what, it's going to get squared. So if this is a positive number and it gets squared, it still becomes a positive number. If this is a negative number and it gets squared, it's still a positive number. So we would say here that the system has potential energy. But where's that energy coming from? Well, someone had to do work to it, right? You had to move the block. You had to compress the block. You actually had to do work onto the block. So this is the two states of potential energy. Notice, all the potential energy is a result of the object being away from equilibrium. The object is at a high state. Does this cart want to stay on top? No. Does the spring want to stay compressed? No. They all want to return to equilibrium. They all want to release its potential energy. Let's look back at this example. On the AP Physics 1 exam, you're going to see this in the FRQ as called qualitative, quantitative. It's basically allowing you to use words and math to describe each other. So remember this scenario when the ball is being compressed and we shot it off and it rolls up the ramp. Now we're going to throw in some values. The ball is actually a 2 kilogram ball and it is compressed by 1.5 Newton meter. That is the spring constant. The compression amount is 4 centimeters. No, it should be 4 meters because this is Newton meter. Yep. Okay. 4 meters, I mean. If we plug it into the formula of the spring, US equals to 1/2 K delta X squared. If you plug it in, you get 12 joules of energy. So we would say that at this point, the object has 12 joules of energy. And we let it go. And remember, now the spring wants to return to equilibrium, right? So there is going to be a force this way. And we know that force is called Hooke's law. So you hear this as the restorative force sometimes. Now the ball starts to move and the ball starts to reach its maximum velocity. Find that velocity. Well, you don't know what the velocity is, but you know that K is equal to 1/2 mv squared. But you know that the energy here has to stay the same. That's where it gets 12 joules of energy for the K. So you have an M, you have the K, which is 12 joules. Now you can solve for V. The V here would be 3.5 meters per second squared. Remember, this energy has to be the same because this system is closed. Okay, it is closed. There is no friction nor drag. Now it's going to start rolling up. As it rolls up, the object is going to start slowing down because there is a gain in what? Potential energy. The ball reaches the maximum height. So find the height value. In this case, it would just be, again, 12 joules of energy because that is what that is. And we know that potential energy is equal to mass, gravity times height. They want to know what the height is. You already know the mass is 2, gravity is 10. And we know that the total energy would be 12. You solve for that, you get H equals to 0.6. There you go. This is how you use a qualitative quantitative translation. This is the math that supports what's happening in the situation. Notice the object stays at 12 joules each time. Now, the AP Physics test always has one form of this question appears. Now they say you sprinkle in some sand or there's some bumps here. So there's some sand or bumps here. Okay. It's basically introducing a friction term here. Once they introduce a friction term here, what is the new height? Well, let's take a look. We know that will the friction affect the spring's potential energy? No, it doesn't. Okay, the friction doesn't. But what happens as the ball travels right here across the sand part? Okay, is it 12 joules? It's not 12 joules. It's actually less now. The reason why is because it loses some here. Let's say it loses some here. So its kinetic energy would be somewhere around, let's say, 10 joules of energy. Where's the other joules going? Well, remember, there's friction there. So we can say there is a thermal energy column here, and we can draw it right here. And this is at 2 joules. That's where it's going. So the system lost 2 joules of energy due to thermal. If the system lost energy, how much potential energy will the system have? Well, we know that it won't have 12 joules. It's only going to have what? Like before, it's going to have only 10 joules left, because that was how much kinetic energy was able to give it. As a result, is the height going to be smaller or lower? Well, it's going to be lower. The ball is only going to reach up here. It lost some of the energy due to the friction. So how would the energy chart change? I already showed it to you. The spring potential chart doesn't change. The kinetic energy does, because the ball lost energy when it went over the friction part. As a result, the kinetic energy, which is a lower value, that means the potential energy for the ramp is going to be lower as well. Another part of the FRQ is the short answer part. Here I gave you two hanging masts. These two masts are equal in value. Please ignore the mass of the pulley and the spring. So what is the object and what is the system? Well, we can say that the objects are the two masts. The system would be the mass and Earth. Is this object in equilibrium? Explain, draw a picture. If I let go of this system, is it going to stay at it where it is? No. You should already know that it's going to go somewhere like this. So it starts from here and it goes to here. Why? Because this is its natural state. The natural state is when both masses here are at the same height, because their masses are actually the same. In that process, there was a change in the potential energy for object X and object Y. Object X went up and object Y went down. Okay, that was where equilibrium was. We would say that object X gained potential energy because it went up. You see the height here was positive. But what about for object Y? This should be object Y here. Sorry. Object Y loses potential energy because now it went down. So where's the energy going? We know that object X gained potential energy and object Y lost potential energy, but where's the energy going? Well, the object X gained the energy that the object Y lost. So is the system open or closed? We would say it is closed because energy was not lost to thermal, was not lost to drag, was not lost to sound. The energy that was transferred was within the system. So we would say it is closed because no energy is coming in or out of the system between the two masses. Work done is by each of the masses. Now we take a look at the spring potential energy here. A block of mass 0.10 kilograms is attached to a spring with a spring constant of 50 Newton/meter. The block is compressed to a value of X equals to negative 0.4 meters, then release. You should see it right here in the graph. So the first question, describe what happens to the block when it is released. Well, is the block going to move? Yes, because the system has potential energy, and because it does not want to stay at its exciting state, it wants to return to equilibrium, it will release its potential energy. We would say that the block's potential energy is at 1/2 50 times delta X squared. That is the formula for spring potential. And that equals to 0.04 joules. That will be converted to kinetic energy as the object moves towards equilibrium. Graph the energy level as a function of the position for the spring potential and the spring kinetic energy. We saw here that the system has a spring potential and a kinetic energy. Sorry, this should be 1/2 mv squared, and this should be spring delta X squared. Okay, so we saw that the potential energy at the start was at 0.4 joules. And in the end, it's going to go to 0. Why? Because this is the process of it converting its potential all the way to kinetic. It's at its equilibrium. So in this case, is it going to go down linearly or exponentially? Well, it's going to go down like this. The reason why is because it is 1/2 kx squared. The x squared gives you this decay term. What about the object's velocity when the block no longer has 0 joules of potential energy? This means when the block no longer has 0 joules of potential energy, it's all kinetic. So that's what I mean. So this is when it's going to be all kinetic. The 0.4 joules of energy is being transferred to the kinetic energy. So you could solve for V here. Plug in the mass, you could solve for V. V equals to 0.89. This means that there is a velocity at some point here. But let's take a look at the graph. Here, what is the kinetic energy when the block's right here? What is the kinetic energy? Well, there is no kinetic energy here. But as the spring gets converted, right, all the kinetic energy is going to be transferred to the final kinetic. So this is kinetic initial, and this is the new kinetic energy. It had 0, now it had 0.4. It gained all the energy that the spring gave it. And in this case, it goes up 1/2 mv squared, so it goes something like this. All right, this is how the graph would look like. Let me code what was red. This was the spring potential. All right, and at this point, you would say that the velocity is 0.89 by plugging into the equation. Now, a student wants to design an experiment to check for the velocity, to check the validity of this answer. What equipment does the student need to obtain this information? Well, he wants to check for the velocity, so you need a velocity factor. Velocity is distance and time. So some students will say, well, just get a meter stick and a timer and you could do it. Well, we have something to do that for you. That is called a motion sensor. A motion sensor can be attached to the end, and it will measure the velocity because it records the object's change in position over time. All right? So there you go. That is everything that you need to know when it comes to potential energy as it relates to the system and the transfer of energy. Remember, potential energy comes from an object wanting to return back to its natural state.